Hello, now we're on to section 10.4, which is the cross product. So there's some similarities with the previous video on the dot product, but also some big differences too. We can kind of think of them both as ways of multiplying two vectors together, but as I say, they are distinct. Okay, so let's leap straight on in with the definition. Okay, so we're going to have two vectors, and now these vectors are going to be in R3. Good point. We're taking 3D vectors now. So we're taking u and v being vectors in R3. The cross product of u and v, denoted with that kind of multiply sign, is given by a vector now. And as a quick note, the dot product that we did previously gave us a scalar. The cross product gives us a vector. Okay, and it's given in this form, and it's a little tricky. There's nothing hard about it, but it's a little hard to remember. So it's u2v3 minus u3v2 in that first position. We've put kind of a minus at the start there, so we have consistency in the order, but then it's u1v3, u3v1, and then u1v2, u2v1. Okay, and we will in a moment see a shortcut, but for right now, as long as we have the formula in front of us, I don't think that's too hard to calculate. And so let's go ahead and just do that. So we take our two vectors in R3, 2, -1, 4, and 3, 2, 5. I just repeated the formula here so we can have it. So we want to find the cross product of u and v. This is the formula we're going to use. And so really then it's just a question of plugging all the numbers in and calculating it. So just looking at that kind of that first entry, it's u2v3, so that's the -1, 5, then u3v2, which is 4 and 2. And so on and so on. We plug all those in. We have to be real careful. An easy mistake to make is to miss a minus somewhere, particularly if you have minuses and various things like that. But as long as we're careful with parentheses, we can calculate all that out, and we get -1327. So as we noticed in the introduction, we've taken the cross product of two vectors, and our output is now a vector, which is different than the dot product there. Okay, so I mentioned that we'd also see a shortcut. So I think this is that same example. So we're going to take the two vectors, the 2, -1, 4, and the 3, 2, 5, and write them under their ijk. So you may recall I was kind of that 1, 0, 0 vector in the x direction, j, 0, 1, 0, and k, 0, 0, 1. So they're really just the positions in our vector. And then we're going to take that, and what we're going to do is repeat the first two columns. Okay, so we have the ijk column, we're going to repeat the I column and the j column. Okay, so having done that, we have those same numbers twice, except for that middle one. And then we kind of draw arrows through going down and to the right and down and to the left. So we start with the ijk at the top and multiply down to the right. So we get I times by the -1 times by the 5. So that's -5i. The j times by the 4 times by the 3 is 12. K times by 2 is 4k. Then we do exactly the same going down to the left with the k and the I and the j. And notice we get the 6 elements there. And if we just go back for 1 second, right, these are kind of the 6 elements we have when we do this cross product. And what we do with those is we take the ones to the left and we subtract them. We take the ones to the right and we add them. So taking the I elements, we get -5 minus 8, which is -13. Taking the j elements, we get 12 minus 10, which is 2. And taking the k elements, we get 4 minus -3, which is 7 in the z. Okay, so because memorizing that formula is a little tricky, this is a nice little shortcut, but it does give us exactly the same values. Okay, some properties of the cross product. It's not quite commutative as we've seen before. So we've seen before with the dot product that if we just switch the order, and we know in regular multiplication, 2 times 3 is the same as 3 times 2. In this case, it's not quite true. It's the negative of what you want. The distributive property, we can distribute the plus with the u plus v there on either side. And then we can also distribute for number 3, we can distribute some scalar, some constant. Can really go anywhere we like. Orthogonality properties, and this will be useful for things we'll see later. U cross v dot u is 0, and the same u cross v dot v is 0. And what that says is the vector u cross v is orthogonal to both u and v. And in fact, I'll say later on we're going to use that fact. But if we take the u cross v, we're getting a vector orthogonal to both of them. Okay, and that's really important. If you cross u with itself, number 5 there, you get 0. You cross anything with 0, you get 0. And then you can take a triple scalar, so you can do v cross w, then dot it with u, or u cross v and dot it with w, and you get the same thing. But order is kind of important here, right? Because if we take the dot product, then the cross product, that's not possible. Right? The dot product would give a scalar, then we take the cross product. Yeah, that just doesn't work. We need 2 vectors. So the order we have within that scalar really matters, within that triple scalar product. Okay, so just like with the dot product, actually the cross product gives us a way of finding the angle between 2 vectors. It's a little different this time. So now we take the magnitude, right? U cross v is a vector, so we take the magnitude of u cross v. That's equal to the magnitude of u times the magnitude of v times the sine of the angle. And that's the angle that's between u and v, and again, the angle will take to be the angle between 0 and pi. And so this is now maximized when the vectors are perpendicular, right? So if we think about the sine. Sine is a maximum when the angle is pi over 2 or 90 degrees. So to maximize that, we'd want them to be perpendicular. On the flip side, if the angle between them is 0, in other words, they're parallel, then sine of 0 is 0, and the cross product will be 0. Okay, so let's go ahead and use all this to find an angle between 2 vectors. So we have our 2 vectors u and v here, 2, negative 1, 3, and 1, 4, negative 2. And then the sine is given by the magnitude of the cross product divided by the each of the individual magnitudes. So go ahead and doing that, and I've just shortcutted it there to find the actual cross product there is negative 1079, and the magnitude of that. Then we just take each of the elements squared and add them together. We also need each of the individual magnitudes, so the root 14 and root 21. And if we divide all that together, so we get root 230 over root 14, root 21. And if we take the arc sine of that number, we get the angle between them. So it's 1.08 radians. Okay. So we can use a dot product, but we can also use the cross product now to find that angle. Okay, one more little interesting aside we can do with the cross products is let's think about a parallelogram. Okay, so in particular, if we're finding the area of a parallelogram, and hopefully you're familiar with this, the area of a parallelogram is the base times the perpendicular height. So it's not the length of that extra side, it's the height that's perpendicular to that base. Okay, so we draw the right angle and we get that height. And of course you can think about this as really just being a rectangle that got shifted. You could take this triangle on the right hand side and glue it on the left hand side and you'd really just get a rectangle. So that's why it's base times height in that way. But what we've seen on cross products might help us here. So now let's define our parallelogram in a plane, and it's formed by these 2 vectors, the vector u and the vector v, and we've put their initial points together. So let's think about that. So the area of that parallelogram would be given by v, or the magnitude of v, the length of v. But it's not quite the length of u, it's the length of u times by the sine of the angle between them. Right? The sine gives us this opposite, which of course is h. So if we take the magnitude of v times the magnitude of u times the sine of the angle between them, we'll get h times by this length here. And that's exactly what the cross product is, assuming we take the magnitude. Okay, so we have 2 vectors and we want to find the area of the parallelogram they form. We can simply take the cross product, take the magnitude, and well, that's about it. So if we take an example, so consider the parallelogram formed by those 2 vectors. So I'll say you take those vectors, you put their initial points together, and we want to find the area of the parallelogram. Well, it's simply a question of taking the cross product and then taking the magnitude. Okay, so again, I've done the cross product sort of as an aside. The cross product is given there. The magnitude is just each of them squared, added together. And we take the square root, and sure enough, the area of that parallelogram would be about 13.75. We can even go one step further. So previously we found the area of a parallelogram. Now what we're going to do is find the volume of a parallelepiped. Okay, that's how we pronounce this word. So a parallelepiped, you might not have seen it before. It's essentially the 3D extension of a parallelogram. So all the sides are parallel with themselves, but the angles are not necessarily 90 degrees. So we have 1, 2, 3, 4, 5, 6, 7, 8 sides that are parallel with each other, and then another 8 and another 8, indicated by the vectors u, v, and w here. And that forms this parallelepiped. So you can basically think about it as a box that's been nudged over and twisted a little bit. Okay. And our volume formula here, again, is actually very simple. So we take the cross product of two of the vectors and then the dot product with another one. Doesn't actually matter which order we do this in. So I have v cross w and then you take the dot with u. I have the single lines outside there. So keep in mind, because the last thing we do in here is the dot product, this will be a scalar. This will be a number. So we just have the magnitude, the simple single lines there, which just means take the positive of that, take the absolute value of that. Okay, and so it's actually pretty simple, right? So we take the three vectors, u, v, and w. First off, I've taken the cross product of v and w, which is given as a vector. Then I'm going to take the dot product of u with that new vector, and I get negative 31. And I'll say that very last step is we take the absolute value. So the absolute value of negative 31 is just 31. So our parallelepiped would have volume of 31 and it's cubic units, whatever the units are now, since it's a volume. Okay, so that's the cross product and some applications of it. As I say, memorizing the formula, it's not that easy, but hopefully the shortcut will help you do it. And once you have that, it's really not too bad. Okay, thank you.